And before we get into the presentation, so update one is that last month we were talking about Steve Thompson. By the way, I'm Bill Tang. I'm co-chair along with Brian Wee for the East of Agriculture and Climate Cluster, because there are probably some new people on this call for today. So Steve Thompson is from the USDA NIFA, National Institute for Food and Agriculture. So he's one of the national program leaders, specifically for agricultural systems. So we've been talking with him, exploring East of USDA collaboration. And one of the initial kind of low-hanging fruit activity we thought we could do is that they have a conference funding program. And so originally we were thinking to have a attached workshop to the East of Summer meeting, July, but that turned out to be kind of short, only some months remaining until the summer meeting. So we decided to do this in the fall instead. So give us some time to better plan this. It will require a letter of intent followed by proposal for a standalone meeting. And the focus most likely will be on something related to wildfires, which is something that we've been touching on quite a bit over the last couple of years. So that's update number one. Update number two, I don't have a lot of update, which is the tentative speakers for the upcoming meetings. So for May, it's still a placeholder. We're still thinking the Nature Conservancy, in particular, having them to talk about kind of a current popular topic, I guess, the nature-based solutions, NBS. So that's in the works. In June, for June, it's still an empty placeholder. So if you have ideas, please let us know. July, we probably will have a meeting, even though it's just a couple of weeks before the summer meeting itself. And that's also a placeholder right now. So again, if you have ideas that you want to cover as part of this group, please let us know, let Brian and me know, and we can work on that. Okay, so you all know that this is being recorded, right? So just so that you are aware. Before I introduce our speakers from Neo4j, you might have seen the book offer, right? And we were just talking about that here. And so if once the link is there, if you scroll down past the abstract in the meeting agenda page, the Google Doc, right now it's just a yellow highlighted placeholder, but so Joanne is working on to get a link there. So with that link, anybody interested in getting the hard copy of the book, you can just click on it and provide your information, your shipping information. Okay, and I've gotten several of these books myself via downloading, so they're quite good. But we're delighted to have the three speakers from Neo4j to present on knowledge graphs for environmental risk management. The full title, abstract, and outline of the presentation in our meeting Google Docs, so you can take a look at that if you haven't read it already. If you've been part of this cluster, agriculture and climate, or have been following its activities over the past couple of years, we've been doing a number of things related to knowledge graphs, concept maps, ontologies, tracing data to decisions. Most recently at our session at the East of Winter meeting back in January, we had demos of using Neo4j graph database to visualize the conceptual connections between various documents related to agriculture and carbon management. So again, we're just so delighted to have the speakers from Neo4j to talk to us about knowledge graphs and Neo4j technology. To make things flow more smoothly, I will introduce all three speakers now, and then they can just hand off to each other with minimal interruption. So first up is Carl Eklund, who's the Federal Account Executive. For 20 years, Carl has worked with organizations in the public sector, helping clients to gain actionable insights from their data and solve data analytics challenges through technology. Prior to Neo4j, Carl held similar federal account positions with information voters, Oracle, HP, and SAS. Our second speaker, Maya Natarajan, is program manager for knowledge graphs. Maya focuses on integrating different technologies to solve complex problems, in particular, championing the use of knowledge graphs to bring context to various systems. Throughout her career, Maya has positioned various technologies, including blockchain, predictive and user-based analytics, machine learning, deep learning, search, and BPM in a myriad of industries at various small and large companies. Maya started her career in R&D in the biotechnology area, focusing on cardiovascular drugs. Very interesting. She holds 5 patents. Maya has a PhD in chemical engineering from Rice University. Our third speaker is Jesus Barraza. Sorry. He's the Europe, Middle East, and Asia Sales Engineering Director. Jesus has over 15 years of experience in consulting and professional services in the information management space. Prior to Neo4j, Jesus was at Ontology Systems for 7 years, where he worked with large graph database deployments in many graph-based projects for major telecommunications companies throughout the world. Jesus has a PhD in computing science from Polytechnica University of Madrid, where he carried out research on graph data modeling and semantic technologies. So with that, I'll hand it off to you, Carl, to end the presentation. You can share your screen.
Thank you very much, Bill. I appreciate it. I appreciate the opportunity for allowing us to present today. The agenda is a brief overview of Neo4j. Some of you may have heard of Neo4j, some may not have, so it's a very quick introduction to who we are. Then Maya is going to go into the most common knowledge graph use cases, and then followed by the understanding the data model and how it relates to other graphs with Neo4j. And then we'll jump into a demo of how to build a knowledge graph. And then we'll follow up with some Q&A and some links to, there's a couple of books, like a couple of Graphs for Dummies books that we have that we can send out if you guys are interested. So that's the agenda. Let's jump into the overview of Neo4j. Again, for those of you who are not familiar, we are the leader in what's called graph technology. We're the creator of the labeled property graph model and the Cipher language. We have thousands of customers worldwide, offices around the world. We have over 400 employees, and we're growing at around 20%. We'll be adding about another 100 employees this year, so we're growing quite fast. And even though we've been around for 10 plus years, we have 20 to 25 top financial firms, 7 out of 10 retail firms, and 7 out of 10 software vendors out there. And we have a huge ecosystem. Just like at the bottom there, 450 events. We have more than one event a day going on. We have quite a groundswell going on around us. And we are quite well established in the federal community. NASA is using us. They claim to have saved over $1 million using Neo4j as a knowledge graph database in order to get the Mars mission. They saved, I think, months and $1 million there. To fighting crime with Homeland Security, to supply chain at Department of Defense, to finding the bad guys and gals at IRS. We're very well established across federal, and we're looking forward to possibly working with you as well. With that, Maya, take it away.
Can you, hi there, hi everyone. Can you hear me now? Perfect.
Yes, yes.
All right. I'm very pleased to be here. And so what I'm going to do is I'm going to start off with this notion that everything is connected. We're all connected to each other, somehow or the other. So the movie 7 Degrees of, it wasn't a movie, 7 Degrees, I even forget. Let's not even go there. Let me start off with, since I'm from California and this presentation is to ESIP, what I figured I'd do was I'd use wildfires as an example to talk about connections. There's so many different areas that pertain to wildfires, from the factors that cause them to their effects on humans, wildlife and environment, to climate change. Within the factors itself, we're talking about nature, such as lightning, to human factors such as lighting campfires or discarding lit cigarettes, trash burning, arson, industrial accidents, energy equipment, causing fires, or even controlled fires that sometimes go awry. So there's so many factors that play, from human factors to climate change. And in this case, we're talking about things like rising temperatures, winter snowpacks melting a month earlier. So, forests are drier for longer periods of time. And there are many, many other factors. So and that's just one aspect of where there are connections. Then there's also the effect of wildfires on humans. That's also connected. Lives are lost. There's pollution. There are increase in costs to contain fires. And then there's increasing insurance rates, right? We need to pay to keep our houses safe, and get some money back in case there's a fire. So see, I've even moved away from the topic of wildfires to talking about insurance. So here we're looking at everything that's connected. Now, of course, wildfires are an example of an environmental risk. And environmental risks are difficult to monitor and manage because they're often connected and interconnected. And it's these connections and interconnections that actually provide context and meaning. So with that, let me go on to this next slide, which basically talks about connections and interconnections are not easy to analyze, and you can't just do it with any kind of database. I'm sure all of you are familiar with relational databases that are used for analyzing structured data. Now, what relational databases do is they strip out connections as they're not well adapted to interconnected semi-structures. In a traditional database, if we try to query relationships, it would really require using SQL, which is not that easy to use, and joins, and they're practically limited to 3 degrees of separation. So they're very limited and time-consuming for analyzing connections. Next, we have NoSQL databases. Now, these were built to store and retrieve unstructured data, things like text, audio, video, and so on and so forth. They do not have language or structure for handling relationships. Okay, joins are done through an application. In addition, there is no ACID. Now, for those of you who are not familiar with ACID, it stands for atomicity, consistency, isolation, and durability. And so there are no ACID, so NoSQL databases lack ACID, making graph transactions impossible. So ACID is just basically a set of properties of database transactions to ensure data validity. All right. Lastly, we have graph databases. These natively store, reveal, and query data relationships. They're meant for analyzing connected data, so they can traverse and analyze any levels of depth in real time. They also add context and connect data to support emerging AI applications, so which I'll describe very briefly in a few slides later. So what is a graph? A graph is really pretty simple. It consists of nodes that represent entities, and here we're talking about things like people, places, things, and events. Now, nodes have labels. In this example, we have 2 types of nodes. We have the people nodes and the car node. And these are connected together by relationships. Now, each relationship has a type. In this case, a person owns a car, or a person loves another person. So here the relationships are loves or lives with, and owns or drives. Now, both nodes and relationships can have properties that further describe them. Example, for the car node here, we have a brand name, Volvo, and the model number, V70. So these are just properties that further describe the node car. We can also have relationship properties. In this case, we have start date of driving, since January 10, 2011. So that's the property that describes that relationship. And these are all key value pairs. A key value pair is when 2 values are connected in such a way that the value is accessed using that key. So why is this important? Basically because it provides fast access to values. So in summary, a graph connects nodes and relationships, and this is a formal way of structuring data for querying and analyzing connected data. So what I just described to you is a property graph data model. Jesus will cover the RDF data model when he presents, so you can see the differences. Okay, so we go from graphs to knowledge graphs. Okay, so I've just given you an introduction to graphs. A knowledge graph is a special type of a graph. Now, if you actually go and Google the definition of a knowledge graph, you're going to get over 100 definitions. So what we like to do at Neo4j is we have our own definition of a knowledge graph. And our definition is as follows. A knowledge graph is an interconnected set of data that has been enriched with semantics so that one can reason about the underlying data and apply it confidently for complex decision making. Okay, so there's quite a bit in here. So let's unpack it and to see what elements make up a knowledge graph. All right. So every knowledge graph is made up of, and I'm going to start at the bottom here, it's made up of data. We all know there are 3 types of data, the structured, unstructured, and semi-structured. Now this element deals with the ingestion of data, and if we use a property graph data model like Neo4j, we add relationships to the data. So I want to start off by saying, just by taking your data and putting it into a graph database like Neo4j, we're adding our first level of context. Okay, the second element is context. And this actually deals with converting data into knowledge by adding semantics. Okay, so, I'm sure most of you in this audience will know that semantic basically means meaning, and that confers context to all things. Now, semantics covers a number of things. Firstly, we have controlled vocabularies, taxonomies, and ontologies. A controlled vocabulary is just a list of predefined terms. A taxonomy is a list of predefined terms plus synonyms, and it provides hierarchical relationships. Okay, a thesaurus is a list of predefined terms and synonyms, plus one level higher as it provides hierarchical relationships as well as associative relationships. And then finally, we have an ontology, which is a list of predefined classes and properties, and it provides expanded relationships. So you go from least complex to very highly complex as you talk about an ontology. And control lists and taxonomies are lightweight, whereas ontologies are heavyweight, meaning they have better inferring power. But it also takes a long time to build and maintain these ontologies. Now, an example I'm going to give you is the suite ontology that you provided us with, and we'll be using that for our demo later today. All right, next we have entity resolution and analysis. Entity resolution is all about determining whether records from different data sources represent the same entity. So let's take my name as an example, Maya Natarajan. Do Ms. Natarajan, M. Natarajan, and Maya Natarajan all mean the same thing? Of course it does, but doing this well at scale is non-trivial. It means comparing every entity with every other entity and identifying it as similar or a duplicate. Now that's a tough problem to do, but it matters that we do it and we do it well. Let's imagine that you're in a business where consistency of your data is key. Your question is, do I have any clients trying to commit fraud, or am I able to detect if someone is trying to avoid paying taxes? This is where entity resolution comes into play, and it allows you to answer these questions. Okay, next we have tagging, categorization, and classification. We all know what that means, what those terms mean, so I won't go into greater detail. And then finally, we have AI. AI covers everything from machine learning to deep learning to natural language processing. In today's talk, I will not go into too much detail about this because it's a rather vast topic. So we will focus on this in our next presentation. And what we'll do is, we'll probably call it knowledge graphs for contextual AI or knowledge graphs for machine learning, and have an expert with us to help us with that session as well. All right, but in terms of context, AI is a very important process of, AI is very important for a process called knowledge graph completion. This is a process by which missing entities and links are added to knowledge graphs. Okay, so in this process, entity resolution is the first step, and then embeddings also play a role. So I'll be talking about embeddings in slightly more detail later on in this presentation. All right, I want to complete this section on context with a, with telling you that context plays such an important role, because this is a step where we're making the data smart. Basically, what we're doing is driving intelligence into the data. And this is how systems and humans can infer meaning from it. Okay, so I finished the first two elements, data, the first element, context was the second element. And finally, we have the third element on the right top, and it's the graph data store. Now, this element deals with using a dynamic structure like a graph to store, manage, and analyze data, and includes graph queries, graph algorithms, graph machine learning, and graph visualization. Now, each element of a knowledge graph is essential, and combinations of elements may be important, but it's only when the three elements come together a knowledge graph is created. So let's look at a combination of data and context. Data plus context equals knowledge. We all know that. Now, if you have knowledge and you put it in a flat structure like a relational database, that's as is shown on the left-hand side of this slide, and then you search for it, you get back the same knowledge. That is the definition of a knowledge base. Basically, knowledge bases have very static, shallow context. Now, if on the other hand, you take knowledge and you throw it into a dynamic structure like a graph, as shown in the top right, you get a structure that's connected contextually to all of its neighbors. And then the neighbors are all connected to their neighbors. The graph grows and grows and gets richer and richer as new information gets added. The value of the graph grows exponentially. So knowledge graphs have very dynamic, deep context. So what are the use cases we've seen our customers using knowledge graphs for? If we had a data spectrum, we can break it down into three types of use case groups. We have the data management use cases, we have the data discovery use cases, and then we have the data analytics use cases. So let's start off with the data management use cases. These focus on data aggregation, validation, and governance. Since data assurance is the motivation, we call these the data assurance knowledge graph use cases. Now, some examples of data assurance use cases include data lineage, data provenance, data compliance, data risk management, and/or mitigation, and data fabric. The next type of use cases are the data discovery use cases. Now, these use cases go beyond simple visibility of information, really focusing on exploration, deduction, and inference of new knowledge. So we call these as insight knowledge graphs. The motivation for these use cases centers around expert understanding and insights. And some examples are what I like to call STAR 360. Basically, it's customer 360, patient 360, product 360. We even had one company talking about agent 360. So we have all these different types of STAR 360s. The next use case example is lessons learned and AML. And then finally, we have the decisioning knowledge graphs. Now, data analytics is all about improving forecasts and predictions and prescribing optimal actions. Although understanding is important here, the ultimate goal is better decisioning. So we call these decisioning knowledge graphs. A few examples are shown here. We have journey analytics, things like patient journey analytics or customer journey analytics. Then we have next best case. Feature engineering for machine learning falls under this category. Churn analysis, recommendations, and fraud. So keep in mind that this is a spectrum, so these use cases can easily blend one to the other. All right, so we just talked about decisioning knowledge graphs, and the one thing that all these knowledge graph use cases have in common is that they require graph data science. And it could be as simple queries all the way up to advanced machine learning. Okay, so first, Cypher queries. I don't know if all of you are familiar or not, but Cypher is the Neo4j proprietary query language. And so when we talk about cipher queries, these are human crafted queries with a human readable result. Okay, so you write these queries based on your domain expertise, and the results of the query mean exactly what you expect them to be. We use these for real-time matching when we know what the data patterns are of interest are. But what if you don't know what if you don't know where to start the query, or if we want to find patterns anywhere in the graph? You'll need to use algorithms for this, as you're going from really local, what we call graph local to graph global. Okay, so algorithms are predefined formulas. They're used when we want to compute over the entire graph or subgraph, and we want to find answers like popular paths or influential nodes. The example given here is PageRank, and PageRank gives you the most influential node, but we have over 50 algorithms in our GDS library, including things like community detection for finding clusters or partitions, centrality for determining the importance of distinct nodes in a network, similarity for evaluating how nodes are alike, and so on and so forth. In this case, there's a formula that's being calculated, but it's still human readable. All right. Now, graph queries and algorithms can both be used to train machine learning models, specifically for feature engineering. But the question we need to ask here is, what if you don't know what to query or which algorithms to use, right? One possibility is you can use brute force and try all the algorithms and then compare the results, but that's an extremely tedious task. So it's better to use embeddings, and that's where embeddings come into play. Embeddings are actually a way of encoding the nodes and relationships into a structure suitable for machine learning. Okay, it's an AI learned formula, and it's only readable by the machine. This is a heuristic that learns a function, and this is custom to your graph, and you tune it accordingly. The beauty of embeddings is that you don't need to know what pattern you're looking for. Okay, but keep in mind that these are not predefined, so they're much slower than algorithms, and they require tuning, and you have to tell it what attributes to look for. So there's obviously always a trade-off, right? It's if you want the more accurate, you've got to do a lot more work to get it. Now, all three, queries, algorithms, and embeddings, can be used for feature engineering in machine learning. When do we use which? If we know what elements are predictive, we use queries and algorithms. If we don't know what elements are predictive, we use embeddings. It's as simple as that. They all function to improve decision in graphs. That's the important part. Now, what's new with Neo4j graph data science is that we also have graph native machine learning. What that is computing machine learning tasks all within the graph database. Now, today you can perform supervised machine learning using the Neo4j graph database, ways to reason about labels and make predictions in the graph. What we do here is we use label data to learn a function and to map out input data onto outputs. So this is just like your general machine learning, except we're doing it within the graph. Okay, and we also take relationships into account. So that's the important thing, doing it in a graph where we take relationships into account, whereas your general machine learning models do not take relationships into account. Okay, so I'll not go into any more depth here because this is a whole session all by itself. My aim was just to let you know that we can do this, and hopefully we can come back with the experts on that side of the house to discuss AI and machine learning further. Okay, so let's look at the architecture of a knowledge graph so that you know where each of the Neo4j components come into play. There are three layers that every knowledge graph has, and I'm going to go from bottom to top. We have the data orchestration layer. Now, this layer deals with data of all types, structured, semi-structured, and unstructured, and the tools needed to extract and transform and prepare data for ingestion into a graph store. The second layer is what I'm going to call the data catalog layer, and this is where data is ingested, organized, enriched, and accessed. Okay, so included in this layer are the semantics, whether it's the control list, the taxonomies, the ontology that I mentioned earlier. Okay, and then in the topmost layer, we have the data consumption layer, and it's all about how data is going to be consumed via the various use cases using graph analytics and visualization. So if we were to actually map the Neo4j products against this architecture, this is what we'd get. All the Neo4j products are shown in red. So you should be able to see that. And it may necessarily not be a product, but it actually, it's not a product, but it may be a tool that we can use. It's a Neo4j tool. All right. For the data orchestration layer, we need ETL and NLP tools. For ETL, we have a number of options, including the Neo4j connector for Apache Spark. So for those of you who are familiar with Spark, we can connect to it via this connector, and HOP. And we also have RDF. We also have, Neo Semantics. RDF is a form of structured or semi-structured data, just like JSON or XML. And so we can use Neo Semantics to import it. Neo Semantics is a plugin that enables the use of RDF and its associated vocabularies like OWL, RDFS, SCOS, and others in Neo4j. Jesus, who's the creator of Neo Semantics, will talk in much greater detail during his presentation and demo. For NLP, we use APOC. These are Neo4j wrappers around Google, Amazon, and Microsoft natural language APIs. These procedures extract entities, key phrases, categories, and sentiment from text stored as node properties. And Jesus will actually be showing you APOC in the demo. In the catalog layer, we have the Neo4j database, as this is the graph data store. And this is where, as I mentioned early on, the ontology will reside. We also have the knowledge graph workbench that includes a Cypher workbench for data modeling, so you can model your data, and then KeyMaker as a pipeline for queries and analytics. And finally, in the data consumption layer, we have Bloom for visualization and GDS for, we have Bloom for visualization, that's right, and GDS for analytics. Now, Jesus will be using most of these products, Neo4j APOC to extract entities from articles, the graph database to store, query, and analyze, Neo Semantics to go back and forth between the two data models, RDF and property graph, and Bloom for visualization for the demo. So with that, I believe I'm going to finish off with 3 customer case studies. Here, what I'll do is I'll discuss the challenge and how knowledge graphs have provided the best solution for each of our customers. The first use case is Lockheed Martin. The challenge at Lockheed Martin was that they wanted to integrate all of their processes and data, from engineering all the way to ERP to procurement, across the entire life cycle of their highly complex products. There were 2 issues that they faced. One was to determine how to connect data across their disparate data storage systems. They had a data silo problem like like all of us do. And the second was to see what connections there were between the data and from these, what the connections were between the data from these various systems. Now, without this visibility into the entire product ecosystem, there was no way for them to gauge the downstream impact of a single variance. Okay, so the solution they deployed was a Neo4j knowledge graph, and they used it to perform an impact analysis to actually determine the downstream result of an issue or a change anywhere in the product life cycle. So all the things that could have influenced a part and what caused it to fail are identified in this process. The question is it from engineering? Is it from procurement? Or is it from supplier? Or is it a vendor issue or a manufacturing defect? So they used Neo4j to do traversals and find variance in the process and report it back almost instantaneously. Now, they were actually doing this manually before they got Neo4j because no other type of database could handle it. And it took them weeks, sometimes months, to get back a result. Okay, the second use case is at NASA. At NASA, the challenge was similar, but in a slightly different area. There's a lessons learned database at NASA. I'm sure all of you are familiar with it, where contributors from across NASA and other organizations, they contribute to this database. However, even when these lessons are, so these lessons that are currently identified and documented, they get lost in a relational database, and so it really prevented NASA from learning from experience and repeating mistakes. Okay, so the solution at NASA was that they deployed a Neo4j knowledge graph and successfully found information on the Apollo project that prevented issues in the Orion project. In this process, $1 million of taxpayers' money was saved, and over 2 years' worth of work was also saved. Now NASA is actually tackling another challenge of finding the right skills within the organization that actually seems to lay hidden within the number of employees within NASA itself. All right, the last use case is an example at a US government agency. We're not allowed to mention the name, but they're using it for fraud detection. They want to find fraudulent patterns in business applications and alert analysts. For this purpose, they've deployed a Neo4j knowledge graph and will use graph algorithms such as community detection and similarity to track synthetic identities, entity resolution, and fraud rings. So with that, I'm actually going to end and hand over to Jesus. Jesus?
Sure. Yeah. Thank you very much. So I think I'm going to just spend a couple of minutes because you've got a great introduction from Maya on what property graphs are and Neo4j, but just to put it in context, because I understand that you're familiar with RDF in the semantic stack. So just there are two approaches that have the same underlying paradigm, if you want. Both represent data as connected entities, as a graph. And the way we see it, you're going to see it in the demo in a minute. RDF is kind of RDF is defined itself as a data exchange model. So it's meant to be a mechanism to interoperate between applications, and that's how we see it. So it's important to understand that the models are slightly different. So you see that the property graph to the left. I'm looking at the model at the bottom. So it's based on nodes and relationships, and nodes have some let's call it internal structure. They have attributes, whereas in an RDF graph, everything is a statement, everything is an edge, right? So you probably see a more kind of anatomic decomposition of your data, and that's intentional because of where they come from. So this is more a logic-oriented type of model. It was conceived as a way of representing distributed data ownership. So it made sense for different fragments of the graph, of the RDF graph, to live in different places. But what's important is that RDF makes no assumption on how the data is stored, is persisted. And you will see in a minute that it is absolutely fine to store data, RDF data in Neo4j, right? So if we move to the next slide, we see that there's a whole lot of publicly available RDF data sources, and that can be in the form of annotated data sets, but also public ontologies, public vocabularies, public taxonomies, even constraints lately, things like shackle descriptions of graph shapes. There's plenty of them, and sometimes they can be accessed either in a bulk mode or sometimes through APIs. Well, both ways are perfectly valid for Neo4j, as we're going to see. And we're going to be able to leverage today the suite ontology. So next slide. And just to conclude, we say that RDF, we can persist that in Neo4j, and we're going to be using the Neo Semantics extension. Neo4j offers a number of extensions that make the experience of the developer, of the technical person that's interacting with the graph, makes their experience easier, in the sense of, in this case, interacting with RDF sources. But also I'll be using APOC that was mentioned before to simplify things like accessing public APIs like the Google Cloud NLP. But you have an example in front of you of what I mean by an RDF graph with its representation. You see how it's one edge per statement in your RDF data set. But when it's imported, we apply a very simple and straightforward approach, which is every literal statement becomes part of the internal structure of a node. It becomes a property, an attribute, as we call it in Neo4j. But object statements or triples that connect nodes will become relationships. Then we have the option to, because we have an additional construct in the property graph, which is labels, to represent type statements in RDF as labels in Neo. And ultimately, and that's a pretty recent extension to RDF that you might have come across or you might have heard about, which is RDF star, which is a way of representing in a compact way reified statements, which is quite convenient. We're not going to go on or use it today, but I thought it was worth mentioning because that's a way of conveying things like relationships in properties, which was one of the traditional limitations of RDF. Good. So yeah, so probably I'm going to go straight on the demo. Yeah, I'll try to touch on as many elements in our portfolio of products. I mean, the extensions to integrate with the different components of the demo, Bloom for visualization, and maybe just mention GDS. But yeah, let's go straight on the demo. So if I can maybe take control, I'm going to share my screen, and please let me know when you can see it. You should see a sketch of the pipeline that I'm going to be running on.
We can see it.
Perfect, fantastic. So that's just 2 minutes to describe the process. So as Maya mentioned before, we're going to take a bunch of articles from a public site, which is about forest fires. And we're going to import them into Neo4j. Actually, it's done already. So we load these articles. And we're going to apply a first step of entity extraction. And for that, we're going to use the Google Cloud Platform NLP API. So we're going to take these articles, which are represented as nodes in our graph, and we're going to extract entities out of them. And we will find that some articles share entities, obviously. And then in a second step, we're going to apply a semantic enrichment step, where we are going to try to actually, we're going to do it in two ways. We're going to use existing ontologies as structured semantic representation of domains, and I'm going to be using Suite, but we're also going to be using, I wouldn't call them ontologies, but for example, categories from Wikipedia, because they also can form informal, if you want, taxonomies. And we will be able to combine both and do things once we have this knowledge graph built, we're going to be able to do things like expanding queries and doing searches by concept, by things instead of strings, and then introduce things like semantic similarity between articles, between documents, or maybe recommendations based on these similarities. So that's the context. Let me show you what I what I mean. And by all means, please do interrupt me if there's anything unclear or you have any questions. We'll try to save some time at the end for Q&A, but still, if there's anything that's not clear, please stop me. So what you have in front of you, especially for those of you who may not be familiar with Neo, is what we call the browser. The browser is the technical person's, the developer's interface where we can interact with the graph. We can write to it. We can visualize it, and I'm going to use it to show you what our model looks like. So, like I mentioned before, we're importing data from this page. I'll skip the process of downloading it because that's relatively simple. But essentially, what we have is a bunch of articles represented as nodes, which I'll show you a few of them. And this query that you see is what Maya was described before, is the Cypher query language. So I'm looking for nodes by type and filtering by articles that mention the word bird. So in that case, it's just any random selection. So you see that articles are nodes, and nodes, if I click on any of them, have a set of attributes, right, which are essentially, in our case, the title and the text, which is basically the abstract. They also keep a reference to the article itself, so we can always link back to the source, and that should take us to the article in the page, right? So that's the first step, the import of the article data. The next step is we said the entity extraction. I'm not going to run it because it involves, like I mentioned before, invoking the Google Cloud Platform NLP API, and that's a bit time consuming and a bit risky for a demo. So I've run it before, but I wanted to show you just the code in case you find it interesting, because what we're doing basically is we're iterating over the articles and just calling through APOC. APOC is an extension, is a set of stored procedures that simplify the integration with external platforms, among other things. And here what we're doing is generating a request to the NLP API, and that is returning us a listing of entities that are detected in this text. And we are creating a graph by extending the article with the entities that are mentioned in that article. So if I rerun the query on birds, but now also extending, returning the entities, and as you can see, all I'm doing is extending the pattern and saying, give me the articles, but also the entities that are connected to it, I can get something like this, which is the 3 articles with some of the entities that are mentioned in each of them. And of course, there will be some shared entities across articles. That makes perfect sense. Good, so that will be the first step, the entity extraction, right? The next step we called the semantic enrichment, and we have the 2 branches. We can do it by getting categories from Wikipedia. One of the things that the Google NLP API does is for some of the entities that are detected, they come annotated with the Wikipedia identifier. So for these topics, we can do this sort of thing. We can go to Wikipedia and to the API and get some additional categories. What do I mean by that? Let me show that to you. And again, I'm not going to go into details, but we're using APOC again, this time to invoke the Wikipedia API. So I'm saying, for all the entities that have been extracted in the previous step and that have a Wikipedia URI, well, I invoke this service and get the categories. And the categories, I'm representing them as concepts. I'm also tagging them as wiki category, and I'm linking them to my entities in the graph. And what I get, again, I'm not going to run this because it's a running process, but the result is something like this. So a subset of the entities that were extracted will link to Wikipedia categories, and that's what forms my first layer of semantic. I understand that this is kind of a lightweight, if you want to call it like that, ontology, but that's the first kind of semantic layer that we get from Wikipedia. And we can also apply that recursively and get super categories and get a full taxonomy. So there's one step that I'm going to skip, but I thought it was worth mentioning. Wikipedia is a pretty, it's a collaborative environment, and it's not constructed as an ontology. I mean, there's no proper ontology engineering processes applied, so there's a lot of redundancy. It's pretty noisy environment. So normally, when we import categories from Wikipedia, we'll have to do some cleansing and things like remove loops, remove redundant links, and these kind of things. But I thought I'd just mention it and probably skip through it. But we now have a graph, right? We have a first knowledge graph, if we want to call it like that. And in this graph that has this shape, articles, entities, concepts, and then concepts organized in hierarchies, we can run queries like analytical ones. They're pretty simple, but we can say which is the most popular concept. And a popular concept can be measured in terms of the number of articles that refer to it. And we know that articles will not necessarily refer to concepts directly, but we have entities, and entities will relate to concepts. So if we do something like this, we can get a listing. First thing we realize is that it's a lot of geographical information, like places, and that's probably the result of the type of entity extraction that the Google NLP API does. And it's worth mentioning that I'm using this one, as I could have used any other entity extraction framework or service that instead of this one. We support the one by AWS, the one by Azure, but you can plug whichever entity extraction library or component that you may want to use. So, right, what all the queries I can do? Well, the idea was being able to do searches for things instead of strings, and this I think this query reflects that in a pretty well. So what I'm doing there is I'm looking for articles that relate to this concept of wildland urban interface. So let me run the query and then we'll try to interpret what that returns. So this returns the visual element, right? So we see that there's a concept, right, which is this idea of a wildland urban interface, and we have a number of entities that actually represent that concept, right? And these entities are mentioned in different articles, and you can see that there's variants. So, for example, it's sometimes mentioned as WUI, sometimes fully spelled, maybe with different spellings or with different acronyms. And the idea is that they all refer to the same thing. So instead of doing a search, a text-based search for WUI or for the whole sentence, which would return partial results, we're now able to do a search, a conceptual search, so a semantic search in a way. And then Neo4j takes care of expanding it. So that's the our first kind of objective here, right? When we build a knowledge graph. So I'm going to take a little pause here and jump to our other way of exploring graphs. And let me copy this other concept. So here, as you see, I've been writing Cypher queries and getting results. But I mentioned before that there's Bloom as well. Bloom is our visual exploration tool. And this is not so much developer oriented, but more business user, if you want, oriented. So what we do, the way we interact with Bloom is by writing, I wouldn't call it natural language searches, but more Google-like searches. So if I say, for example, I'm looking for entities that for a particular concept, which is the one that I've copied in the previous page for coastal sage scrub, right, as random one. And you see that Bloom is understanding what I write, because Bloom is model aware. Bloom is aware of the fact that there's a notion, there's a concept that's an entity in our graph, that there's a relationship called for concept, and that there's we can even do a full text search for this coastal sage scrub. So it's translating for me my close to natural language sentence into a graph pattern. So if I'm happy with what I see, I can select it, and then I get a result for this search. And effectively, I'm getting the two entities that are represented by that concept. And here I can do similar things to what I could do in the actually a lot more than what I could do in the browser, because we can have more advanced visualization, some sort of hierarchical view. But again, the interesting thing is that we have access to all the details for every article. We still can access the content. We can even link to the URL, etc., etc. Right. So we have a first cut of our knowledge graph, but we said that we also wanted, before I bring the suite ontology, because we kind of have an ontology somehow. I mean, I was saying that probably calling this an ontology is stretching it a little bit, but we have fragments of knowledge, if you want, explicit knowledge. Like one of the things that we extracted from Wikipedia is the notion, the concept of ethnic groups in the United States. And we found that, well, that there are two subcategories, which I represent with narrower than. That's my choice. I can, in Neo4j, I can use my vocabulary. I could have chosen to align to standards like well, subclass of in OWL, but I use this more SCOS sort of terminology, because it's a sort of a lightweight hierarchy. Let me pause for a second, because I realize it's nearly the top of the hour. Do we have a hard stop at the top of the hour, or can we go on for a few more minutes?
Yeah, we can go on for a few minutes. Yeah. Okay,
perfect. I'll try to keep it short. But
okay, thanks.
Right. So we have this kind of ontology, which is small fragments, and we're going to bring suite in a minute. But because we have that, we can run inferences in a way. So we can do, and we have this element of inferencing in the Neo-Semantics or NTNS library, which is another extension like we mentioned before. So I can select a concept pretty much like I did before, but instead of getting entities that refer to that concept, I can navigate the narrower than, the subclass of this hierarchical representation for additional elements. So there's nothing in my data set that explicitly describes this article is about ethnic groups in the United States. But if I run this query, Neo4j will find that these entities actually represent concepts that are subcategories, as we can see, narrower than this notion of ethnic groups. So we're kind of effectively embedding that knowledge in the graph and using it for expanding our query and running inferences. So articles that don't explicitly mention that concept, but effectively relate to it, are being returned. So that's the kind of thing that we can do once we build the knowledge graph and we've encoded this semantic knowledge. Let me jump quickly to the second approach. We said that we were going to be importing an ontology, and I'm linking here to the well, I'm not going to describe the suite ontology for you because you built it, but as you know, because it's very modular, I'm taking this fragment of it, which is the ontology, the phenomena reaction that includes actually wildfires. So I thought it would be a relevant one for our data set. So one thing that we can do after we configure our database to import RDF, and I'm going to skip that step, I can say, well, let's have a look. And I'm using Neo-Semantics for this transformation, which is on the fly. All I need to say is import this ontology. Actually, let's do a preview before I input. And this is where we can find it. And I'm passing the URL for this ontology that I just showed you, and the serialization format. It's written in Turtle. So if I run this step, it's streaming it and telling me, well, these are the classes that I can find. And again, it's already applying the same terminology that we saw before, right? So we see things like a chemical reaction. We see that one subcategory of chemical reaction is a fire, and then even narrower is a wildfire. So I'm applying on the fly this transformation of subclass of, as it appears in the ontology, into narrower than, which is my kind of custom, if you want, vocabulary, the one I'm using in my knowledge graph. But like I say, I could have aligned with the RDF standard. So all I have to do is say import. So if I'm happy with what I see, and I am, I can say, go ahead and import. The triples have been persisted. Now we have them in our graph, and we can, we need to link the suite ontology, which is already loaded, with the existing instance data that we have, right? And the way we're going to do it is by passing some RDF. I mean, one way you can see this fragment of RDF in Turtle here. All I need to say is there's one concept, one category in the suite ontology, which is wildfire, which actually I'm going to say that the way it links to my existing data set is that wildfire, as defined in the Wikipedia, which is the way my data is annotated now, is a subcategory of it. For example, I mean, these don't take this as a very formal approach. I'm more interested in giving you the tools, the approach to deal with this kind of ontology linkage than trying to build something correct. So if I say that this is a subcategory, that's the way the two ontologies link, I can import it again using Neo-Semantics. I can do the same thing, same preview. In this case, instead of telling that's where you can retrieve that RDF from, I can pass it in line as part of the request. That's what this is going to import, a very simple link saying that wildlife, as described in the suite ontology, is a supercategory of wildlife as wildfire as described in my data set. So if I'm happy with that, all I need to do is import, and that will import the single triple, all good. And now we can essentially query our data set, and I'm going to keep it short, but now let me cut that here. So because the chemical reaction, for example, category that comes from suite is already in my graph, and all its subclasses, including fire, And fire, remember, that had wildfire, and wildfire, we just linked it to our data set, and now it connects with the subcategory to the wildfire as described in Wikidata. It now links to all the rest of our data. So I can effectively do a query based on this notion, on chemical reaction, basically a query based on sweet. And if I run it, it will hopefully return some results that, again, they don't explicitly mention that notion of chemical reaction at all, but they mention wildfires. And because Neo4j knows, well, Neo4j knows, we've made it explicit through an ontology that a wildfire is a subcategory of a fire, which is a chemical reaction, then we can infer, we can derive that these are valid responses to my search. I'm going to take a break here. Apologies for the speed, and I understand it's been pretty, squeezed, but let me bring up these final slides so that Carl can conclude, and we can maybe take some questions if you have any. Thank you.
Thank you very much. That was fantastic. Are there any questions? I know we're running a few minutes late. I apologize. Is there any questions on what you've seen today?
Carl, this is just a quick comment before you wrap up. But Jesus, what you just presented was very relevant, because as Bill, Ting, and a couple of other folks on this call will know, some of us were experimenting a few months ago actually with what you demonstrated in terms of extracting concepts from articles and looking at the relationships. But unfortunately, we meaning me, I did it in a very clunky manner. So it was very interesting to see you do all that very elegantly and in a manner that is repeatable, because what I did, a whole bunch of Python code, it's not quite scalable. But so I just wanted to say that what you did was very relevant to what we were thinking about, because in that experiment that we tried, it was about carbon management. We were trying to extract concepts related to carbon management from articles. But as Bill will know also, we are still our group is still looking into wildfire issues, and Bill and I have thought about running a similar process for extracting concepts from wildfire articles. What you presented was actually right on spot, and so that was a quick comment that I wanted to put out there.
Excellent. Thanks. I'm glad to hear.
So guys,
sorry, yeah, go ahead.
we do have some, oops, sorry guys. We do have some questions in the chat window. I believe Charles said he had a question. Charles, do you want to go ahead and ask your question?
Sure. So just more of a comment. So I'm part of the ESIP Semantic Tech Committee and also the ESIP Harmonization Cluster. So we're part of the actual developers of the suite ontology, and then also creating crosswalks to the environment ontology Invo. And so I guess one of the questions I have as far as, being an ontology developer and trying to enable applications such as this, first of all, if you would have any suggestions on things that maybe we should do. So one of the things, and actually you can comment on this, one of the things that we're probably going to be doing over the next year, we already are doing it in some ways, is creating, sort of what's called a switchboard, crosswalk to other concepts in Wikidata and Invo, mainly using SCOAS, but in some cases using some RDFS, more formal logics, to enable essentially building those larger connections and knowledge graphs. So that's one of the things we're doing. But I was wondering if you would have any comments on other things that might be useful to enable applications like this to consume both suite and other ontologies that are being developed as part of ESIP.
Yeah, no, that's a very interesting one, and it's something that we come across quite often, and we've published some, similar to the experiment that I've run today. This type of pipeline where you start from unstructured data and you bring some entity extraction, and then you start overlaying. So this idea of combining multiple ontologies is a very common one, and we find it very useful, like we've shown here in query expansion, but I didn't have time to touch on that. But yeah, it can be also used to do similarity. That's a very powerful. There's a number of semantic similarity algorithms out there that leverage the graph structure. And there's many. I mean, all these to say that yes, that's what we see as the right approach. I mean, we understand that different ontologies. I mean, even using portions of ontologies is an approach that makes perfect sense depending on the case. So my recommendation there would be to I don't know if in your case you have a clear use in mind, or you just connecting knowledge in order to build a corpus of connected entities. Because if you have the use case in mind, I think that's in my opinion, that's a particularly important element, because that will drive the way you build your knowledge up. So
both. I mean, we have competency questions. Obviously, ontology. I'm an ontology design patterns guy, and so we try to, when we're doing these harmonization events, at least have some grounding. But the ontologies are also general services to the ESIP community, right? I mean, that's why ESIP hosts these things. And so it in some ways is broader than that, because Suite is a fairly old ontology, right? And has very, very broad application across the earth sciences. So that it's sort of a double-edged approach, right? But I think that enabling these sorts of the signals that you can get from the machine learning that you were talking about, I think, is an important use case that we've been talking about in these clusters. So, by the way, Jesus, I am a Twitter stalker of yours, so I think we probably retweeted each other at various points in time. So.
That's great to know. And I mean, one of the things, as you know, probably is that Semantics is what we call a labs project, like APOC is and some others are extensions of Neo. And what that means is that we have a good level of flexibility in terms of driving the roadmap. And you probably have noticed that recently we've included things like shackle shape description to doing graph validation. We're extending our inferencing capabilities, and we really want to hear from the community and from users like you, your team. What would be useful? What would it make sense for our team to spend more time on one front than the other? That's why I'm really interested in hearing more than what approach to take. Is how are you expecting your teams to use the ontologies that you're building, that you're linking for, and that can be extremely useful for us to drive the roadmap and also for you to benefit from evolutions of Semantics.
Yeah, I mean, I think this is a very important conversation. I mean, I think one of the biggest things you've done is RDF Star, right? So I think that enabling, essentially seamless transport between, the representations, I think is very important. So, and I see, most of the other graph vendors, I think we would use GraphDB. And so there's a community ontology repository that serves Suite that's maintained by ESIP. So it's a semantic resource, triple store that maintains these things that ESIP provides. And I'm sure that the next version of that supports, RDF Star. And so I very much see these as, the community being able to more readily consume and do really, really interesting applications with the work that the ESIP community is doing. So I think that's probably one of the big things. But I think there's also a broader conversation, which would be nice to continue. I think this was fantastic. Unfortunately, I didn't see many of the semantic community people here. It was sort of probably not able to make it. So, but I think that would be also an interesting conversation within ESIP to continue if you guys are willing to do it.
I'm sure, yeah, and of course I leave that to Carl and Joanne, but more than happy to have a follow up if to put the focus on the topics that are relevant to your team. But we can have a because again today we touched more on how we consume public resources, but there's the other angle on how we can make a Neo4j graph public as RDF, and that's where we are kind of a provider of RDF star data sources, because I know the platforms are supporting it, but there's not many public RDF data sets out there. And
Yeah.
some of the rich data that we have in Neo4j can be published as RDF star. And that's another interesting angle that, but anyway, probably too much, but I don't want to.
Sorry, I hijacked your.
No, that's great.
Hey, Jesus, there's one other question which I thought was really interesting. It's from Armin Mehrabian. I hope I pronounced your name right. Does picking RDF or property model have any significant impact on the speed, like query latency?
You mean the difference between one? I think this needs to be answered from the point of view of the data store. Like I mentioned before, RDF is a model for data exchange. So I've shown how we can store RDF data into Neo4j. So once it lives in Neo4j, you benefit from the native storage of Neo4j and the speed and the performance of Cypher and the declarative nature of it. So you get all these benefits. I don't know if the question is in the direction on and that performance, you get it whether that's a graph that comes from importing CSV files or RDF. It doesn't make sense. I mean, it doesn't make a difference. Sorry. Once it's in Neo4j, you have that speed. I don't know if the question is more in the sense of would you get a similar performance if you store the RDF in a triple store? I think that's a different one. And without going into too much detail, triple stores are well, you've seen what triples are like. So it's basically a record with 3 columns. Maybe you can have a fourth for named graphs and context, but it's a very strongly index-based type of storage. And the way you do deep traversals, for example, which is one of the queries that we've been running today, is still by doing joins. So you will suffer from this kind of performance penalization from this index-based storage. So again, this is a simple answer for a complex question, but Neo4j is a native graph store in the sense that it persists connections, and then you get lightning speed traversals because you don't do joins, you don't need to scan indexes, you're just chasing pointers, and that's significantly more performant. But yeah, I mean, I don't know if that answers the question or that brings more confusion.
I think there's one other question. It says, how is time and changes with time represented?
Well, we don't impose any particular, I mean, first of all, Neo4j is not a version. By default, data is not versioned in Neo4j. So it's transactional, and you can add and remove bits of information at the node level, the property level. But then how you store versions and time, it's entirely up to you. So we don't impose any particular model. So if you want to use things like the time ontology, since we're talking about ontologies, you can apply that model and store your data according to that ontology. But it's, again, entirely your choice. And of course, there's some modeling patterns, some recommendations, but it's ultimately the modelers, the data modeler's choice how that's done.
Maybe just a quick, I just want to clarify. So what I had in mind was the properties of a node can change with time.
Absolutely.
So then how does that get incorporated in the...
Right, so the first question exactly is what's the granularity of your versioning. So and if you want to keep track of changes in properties, I mean, normally what you have to do is you have to create a node that represents the value of the property. And then you can have, for example, a chained list. You can have a sequence of values. That's one possible way. You can also use, you might want to version at the graph or subgraph level. So when there's a change, you replicate what's the frequency of changes and what portion of the graph is affected by changes. So you may want to replicate portions of the graph and then have them annotated with the version or with the timestamp. So the answer that I would give in the general case is that the model and the pattern that you apply is entirely driven by the type of use of this versioning data. If you want to detect deltas and be able to compare two versions of the graph, you want to represent it in a way that allows you to do that. Yeah, very hard to give a categorical, if you want, answer, but there's different patterns for the different cases. I mean, we mentioned before that I've done quite a bit of work in the telco space, and that's a very general problem. For example, when a network changes, it changes in structure, but it also changes in attributes, and depending on the case, for example, when the topology of a network changes, that normally happens in what they call in change windows, in batches. So maybe the change happens every week, but then a significant portion of the graph changes. So what they decide to do is to replicate the whole graph with a new version. And you can still query across and detect deltas, but you query always the latest version of the graph for things like impact analysis, root cause analysis. So you always want to have a fresh latest version. And I think I'm talking too much, but you know, as you can see, there are different options for representing time and versioning in a graph. That's maybe another topic that we can touch in a follow-up version with some examples, because different models enable different types of ways of consuming the data.
And just a quick comment, I guess we're running out of time, but maybe in lieu of the, given that we are, I presume we're going to close soon, any follow-up further conversations, you know, of course, they can occur outside of this time, of this period, because we normally have this for the agriculture and climate. But as Charles was saying, if the Semantics, the ECIP Semantics Technology Committee has an interest in following up with you guys, you know, again, the conversation can be had in any number of different time slots, not just this slot that we typically use for the agriculture and climate.
Yeah, feel free. This is Carl. I have my email up on the screen. If there's any follow-up questions, please let me know. Or if you wanted to email me about getting any of the graph for dummies or graph data science for dummies or anything, let me know. I can send you any other links. And I think, Bill or Brian, are you going to make the recording available, I think, to anyone who, so they can reach out to you for the recording?
Yeah, the recording will be made available shortly afterwards.
Okay.
Along with the slides.
And then, yeah, if we want to follow up, if someone wants to have more deeper dive into machine learning or anything else, please, you know, let me know directly, or let Brian or Bill know, and they can let me know.
Okay, yeah, so we are 4:21 I have on my clock, so we probably should wrap this up. It's been fascinating discussion, you know, in the presentation. So really want to thank all the speakers from Neo4j, Carl, Maya, and Jesus. Any last minute comment before we wrap up for this afternoon? Hearing none. Yeah, so again, thank you very much. Definitely something, a conversation that we would like to continue with you guys. I think there are a lot of common interests here, I think, obviously. So,
very good.
Thanks everybody for attending.
Thank you.
Yeah, we will follow up with everybody, okay?